So good morning, good afternoon, everyone. So we are starting our sixth webinar in a minute. So we just started with sharing our screen, and then we start the actual webinar. Just 1 minute. So welcome, everybody. I think you can properly see my screen. We are here again for our sixth webinar for the Emeralds project. Today we're talking about the use case of Riga. So the title of the webinar is Rethinking Urban Mobility Data-Driven Approach to Multimodal Traffic Management. I'm welcoming you. This is Marialetizia from Trust IT Services, the communication dissemination leader and the webinar moderator. But I pass the floor immediately to the project coordinator, Konstantinos Dafloukas from Inlecom, for a brief interview of the Emerald project framework and its overall objectives. After his welcome, there will be the contribution from Sascha Hoogendoorn-Lanser from TU Delft, who is the work package use case leader, and then the contribution from the Rotterdam use case deep dive and implementation insight from Erik, from ARANE. The Q&A session will conclude the panel discussion. So I give the floor to the project coordinator, Konstantinos Dafloukas now.
Yes, hello everyone. Thank you, Marialetizia and Sarah, and generally the Trust IT team for organizing this event. Yes, we are here for the webinar number 6 of Emeralds projects. Rethinking urban mobility, data-driven approaches. We're here with Sascha and Erik from who are coordinating the one pilot for the validation of the Emerald services. Let me share my screen. So yes, Dafloukas Konstantinos, project manager, and presenting this content on behalf of Inlecom Innovation, who is the project coordinator of the Emeralds project. So what is Emeralds about? It's a real project started in January 2023 with the end date on December of 2025. It's considered a research and innovation action project with a duration of 36 months. 19 partners from 10 countries with coordinator Inlecom Innovation. So the Emeralds vision, what's about? The Emeralds vision is to design, develop, and create an urban data-oriented mobility analytics as a service, the well-known MaaS toolset, consisting of the so-called Emeralds that will enable the stakeholders of the urban mobility ecosystem to collect and manage data that are considered of high volume and high velocity, high variety. Here is a list of the consortium compiled of several partners from industry and academia. So here in this project, we have, as I detailed, an urban data focus mobility analytics service as the whole vision. That has led to an efficient and interoperable and easy to deploy toolset able to harness the untapped potential of extreme urban mobility data. So in a few words, we are able to through the well-structured architecture of emeralds to collect and manage data of high volume and high velocity, reduce data ingestion times by pairing data streams, analyze data with real-time responsive AI/ML algorithms, visualize the results in interactive dashboards and enhance visual analytics, and perform sensitive data analytics tasks in situ. Of course, all this service takes place by implementing privacy preservation techniques at all the layers of the architecture. About today's use case, it's a crucial use case for the validation of emeralds as it's it's in the core of the whole project with the multimodal traffic network management. That is working on the development, on the design and the development of multimodal traffic modeling and prediction module comprised of tightly coupled processing elements. With most important features, the extreme scale data collection, self-tuning of traffic control algorithms, mobility AI-driven data fusion, and predictive analytics. So that's it from my side. Now I'll pass the floor to Sascha and Erik.
Okay, then I'll go first. Try sharing my screen. Sharing, yes. Hopefully it's, yes. And again, it starts with the last slide instead of the first one, but come on, what are you doing? Why aren't you doing what I want you to? It's for some reason extremely slow. Then we'll do it like this. My apologies. Today's topic, from reactive to predictive approach for transportation problems. If you have just a first step of congestion or a location is starting to become crowded, it's good to notice that as quickly as possible and to be able to respond to that. And in that case, we can either minimize or manage the problems as much as possible. Let me show you what I mean with that. Why aren't you? Okay. What we're doing, I'm in charge of work package 5. Sorry that I forgot to introduce myself. Something else was bleeping here. My name is Sascha Hoogendoorn. I work for the Mobility Innovation Center Delft. And in that center, and in my role as director, I tried to set up projects that are combined companies, researchers, as well as local and regional governments. And we look for innovations to improve our transportation systems and make it future-proof. And the Emeralds project fits extremely good in the goals that we have for our center. And that's making the step from being reactive when it comes to managing traffic problems to being much more proactive, taking measures quicker as possible. What are we doing in the use case that I'm in charge of? We're looking at the applicability and the potential of the emeralds that are developed within the project with respect to extreme scale data acquisition, processing, management, analytics, and visualization. What we have done, not just us, but together with the rest of the consortium, we selected 3 use cases, all in the realm of urban mobility. And we chose them in such a way that we have the opportunity to demonstrate the broad range of different emeralds that are being developed as part of the project. Also show to the stakeholders in the cities, but also potential stakeholders throughout Europe, what we can do with this. If you look at the use case, and I'll show them in a minute, you will see that the use cases differ in terms of the types of data that are available in these projects and also relevant for the project, the availability of data sources, the type of application that we're looking into. Sometimes we simply want to estimate the current situation. We want to make predictions just 15 minutes to an hour ahead, or for a longer period of time, 7 to 10 days ahead. We want to use it for policy analysis. All of these aspects are coming back in the different use cases. And I think in that case, it's an excellent opportunity to test the different emeralds that that are being developed in the project. Yeah. The first use case that we're looking at is risk assessment, prediction, and forecasting in case of crowdedness in The Hague. I'm not sure if you know the Netherlands, but on the seaside of The Hague, we have the area called Scheveningen, and on a yearly basis, millions of people visit our lovely beach. But it's not just busy on the beach, it's busy on the boulevards, it's busy in the parking garages, on the routes leading towards these garages and the beach. But also, if you look at our cycling network, as well as at our public transport network. At the end of the presentation, I will give you a sneak preview of results that we have obtained for this use case. And I also like, if I forget, to invite you for Friday afternoon for a webinar specifically devoted to this use case. The second use case is about multi-modal integrated traffic management in the city of Rotterdam. In this case, we're not just looking at one group of travelers. We're not just looking to car traffic, but also looking into public transportation as well as the cycling traffic. I won't say much about this. Erik-Sander is about to present about this use case and all the emeralds that have been used. Next week, we're going as a team to Riga to visit our local stakeholders, and there the focus was mainly on public transport trip characteristic inference, and traffic flow data analysis. And here they're much more focused on the policy impact of the work that we have done with the emeralds. I'm not going to through this slide in detail. What is important, and also Konstantinos told us at the beginning, we're in the last stage of our project. We started January 2023. By now, all of the emeralds have been developed, results are getting available, and currently we're focusing on evaluating the results, and the results will become available for a broader audience during the second half of this year. We're not just looking at these use cases, we also have 2 demonstrator sites, and also there they will check how the impact of the emeralds will be. If I talk about assessment, I talk about 2 types of assessment, or more types of assessments. For example, how the software performs, but in our case, we're much more focusing on the real impact that the emeralds have, and whether or not the information that we get out of the emeralds have the right quality and can be used in that case. So we have made a generic assessment methodology, and like I said, on the one hand, we look at software performance assessment, and we want to see if the type of information, like I said, that the emeralds are producing are in line with the objectives that we have in the use cases. And as much as possible, we want to validate the information coming out of the emeralds against the ground truth. And like I said, on the other hand, we have the business performance assessment. I also like to call it more social impact, or a bit broader than that. And there we want to see how it benefits all types of different stakeholders. And if I look, for example, at the example that I just mentioned about Scheveningen, that can be for our local police, for our local city, but it can also be for the shop owners in the area, as well as for the people visiting the beach. Not all of the emeralds can be implemented in practice. We don't need to, because this is not a TRL 7 or higher project, but that does mean that if we're looking at business performance, that we cannot measure that always in practice, but we're going, and that's already scheduled, to talk through different scenarios with the different stakeholders that we have in the different locations. Like I said, if you want to know more about the Hague use case, come visit our webinar upcoming Friday, the 27th of June. It's from 2:30 until 3:30. And like I said, it's about the crowd predictions. And now my last slide, just to warm you up a little bit. These are the first assessment results that we have. What we're looking at, for example, is how well the predicted peaks, the amount of people that you expect to be within Scheveningen, how that relates to the real number of people being there. So the blue line is in this case the forecast, and the orange line is the ground truth. And we're going to do this for the crowdedness, but we're also going to do that for the amount of cars parking in the several parking garages around Scheveningen. So we're looking at the height of the peaks, for example, but also whether or not we can determine when the peak will precisely happen. This is just one of the few first assessment results. So if you want to know more, please join us on Friday. And now I want to give the floor to the topic and the person that the day is really devoted to. So Erik-Sander, go ahead.
Yeah, thank you very much, Sascha. But first, let me thank you for your presentation about all the use cases and having a very great overall, overview of the use cases. And thank you for introducing also the webinar on Friday. That now I want to properly give the floor to Erik-Sander Smits for the core of this webinar, which is about Rotterdam use case deep dive and implementation insights. So I'm very glad to introduce you, Erik, from ARANE. So Erik, if you want to share your screen, you can, I can give you the floor and you can start your presentation. And thank you for now.
Yes, thank you. So my name is Erik-Sander Smits, indeed, from ARANE. We are an advisory company in traffic management, and we are the use case leader for the second use case, which is Rotterdam. And today I want to tell you a bit more about multimodal traffic management within the city of Rotterdam and how Emeralds has helped us to improve by a data-driven and AI-driven approach. So what I will tell about today is that first I will introduce the city of Rotterdam, their multimodal problems and their multimodal policies. Then I will tell you a bit more about the automated traffic management system that's used there. It's the AFM system, and it's used to manage the safety around one of the main tunnels in that crosses the main river in the center. The next topic will be about queue estimation and data fusion, where we use floating car data and intersection data to replace expensive radar data that's used now for the AFM system. The next topic will be multimodal intersection analysis based on policy and network frameworks, where we combine the policy and the data and come up with large-scale analytics to do multimodal assessment of intersections. And finally, a bit of a sneak peek into what can be done with highway traffic forecasting about congestion propagation and breakdown predictions on highways. So to start with the introduction for Rotterdam, Rotterdam is the second largest city in the Netherlands. It's a harbor city, and it also comes with some challenges, and therefore it has some guiding principle that it uses to settle their traffic management. So first of all, they want to make way, they want to make space for pedestrians, cyclists, and public transport in the city, and especially around the city center. Next is that they want to have safe and healthy streets. The third thing is that they want to enhance the choices of mobility. They want to help the citizens to make more healthy and sustainable choices. And finally, they want to have clean and efficient logistics. They do not want to have a lot of large trucks in the city center, but try to electrify as well the logistics within the city. So that's what their vision is based on mobility. And then, of course, there is a transition in mobility, and that's also something that's already quite visible today. So if you look at the data, there is a lot of mobility around the city center, and also the mobility is growing. But what you can see is that the share of private car use is decreasing, and also the forecast is that it will decrease, and the use of bicycles is increasing, and also the share of public transport is also increasing a bit. So that's also, so this is a transition that's going on in the city, and you also want to facilitate this transition and make sure that also the active modes and the public transport get enough space to actually also make all these movements happen. So that's quite important to have as well. Therefore, they changed their priorities. They, as I said, they make more rooms for pedestrians and cyclists, and they did that by adjusting their priorities. So on the left, there was the bus priority where the car was on top, then they had public transport, then there was bicycles, and lastly it was walking. And now they actually completely changed it. They have their slow mode, their pedestrians on top. They are the most important. They should be facilitated the most. Next is the bicycles and cycling within the city, which is really important. Then you can use the public transport. And finally, if none of those modes suit you, then you can use the car, and also the logistics are there. But they have the lowest priority at the moment. So that's how the policy has changed towards a more active and public transport oriented use of transportation. So how does this fit in what we have built for Emeralds, what we did for Rotterdam? It's basically all about multimodal traffic management. So it's about how you can implement the priorities that you have in your mobility vision. How can you put it on the streets? And one of the main things that we are working around is this adaptive flow management system around the mass tunnel that I already mentioned before, which is a completely automated system which can be improved by having better estimates and predictions. Also, the city is looking more towards multimodal traffic management instead of just car-oriented traffic management. So there's a vision and an ambition to bring that towards more multimodal schemes, and also help them translating their policy objectives into maps and networks that are really usable when you look into the implementation. So on the scheme on the right, there are two main blocks. First of all, there's the integrated network management. The integrated network management consists of an offline part and an online part, where multimodal traffic management is established. And this is on the offline part, you have network analytics where you look in the system, you're going to hold it against your policy, see where there are problems, and then you're going to design and configure systems and solutions, and then you monitor how those projects work and how this is going on. So this is more like a project setting, a long-term process where you make decisions based on your data-driven analysis. On the other hand, there's also the online real-time traffic management, where you have real-time state estimation, where you have real-time systems that identify where there are problems in the network, identify bottlenecks, and then there is a network management control. And this is something that's what I will show later for the AFM system. It's completely automated, but of course there's also the control room where manual measures are taken to improve the performance of the transport networks in the city. So how we are going to establish this? So we have emeralds in place, and yeah, it's also consisting of 3 blocks, and the starting point is the car-oriented car traffic part, but the ambition is to bring that to multimodal solutions that also include public transport and bicycles. Then on the top we have traffic state estimators, that's estimating how the current network performs, speeds, flows, queue lengths, for example. It can be about public transport punctuality or waiting times for bicycles and pedestrians. And that can be input on how you're going to analyze your network. So in the middle, we have the large-scale automated network analytics. It's where we try to automatically identify bottlenecks. It's how where we're going to calculate the characteristics of the bottlenecks. We want to calculate some statistics. How often are they recurrent? What is the size of them? What's the duration? So that's all important to know. But what's also important to know is to know where is residual network space. So, for example, if I'm going to reroute traffic to alternative routes, I have to be sure that there is available space on those alternative routes as well. So that's also important to know for that. And then the traffic state estimation and the network analytics is especially flowing towards your offline analysis, where it's your input for your data-driven decision making. On the other hand, the bottom box that we have here from the emeralds is the traffic state prediction, and that's more or less the same as the estimator. You want to get the same indicators, but then you want them to have them for the future. And if you can have a prediction, you can anticipate on future breakdowns, on future events, and instead of having a reactive traffic system, you can have a proactive system that already anticipates on future situations. So that's also something that can help the real-time analysis. So what's now especially in this network analysis? What are we doing there? So there are 2 main inputs. Foremost of that is the data. Of course, you need the data for all different types of modes, and you need quite a high quality to get good results. On the other hand, there is a policy. So policy is, for example, a network or a map of your car network, of your public transport network, of your bicycle network, where you have functions defined. So, for example, for the car network, there are highways, but also urban corridors. They have different functions and also different quality requirements. And those quality requirements, those are defined in your reference framework. And if a quality requirement is not met, if you're not able to get towards the norm, then you automatically have a bottleneck. So the reference framework defines when you have a bottleneck somewhere in your network. And given that, you can do what's in the middle, you can do those network analytics. And you can do network analytics at different scales for different modes, and it has different goals. So the scale, you can either do it top down or bottom up, but you have for each of the different intersections or road segments, you can do analysis. You can look at a larger corridor or a route, but what's also interesting to see how sub-networks or the whole network is performing. For sub-networks, it's, for example, the city center or the combination of all the highways, and you want to see how they perform. Of course, you can do this for all the different modes, and also the interactions between modes are important. So it's not a single analysis for each of the modes, but you want to look how they interact with each other. And the goals that you have for those network analytics is either it's policy monitoring. So is the network performing according to my reference framework, or is it exceeding the norm somewhere? Another goal can be to find the causes of the bottlenecks, the seeds, so to say, and you want to know why problems are happening, because if you want to take measures, you also need to know what the cause is. So then, of course, you have the relationships between bottlenecks, either in time or in space. You can see that there can be interaction between a public transport delay and some extremely long queues in the car network, and you want to be able to assess those relationships in time and space with your analytics. You want to know the severity and the frequency of your bottlenecks and the seeds that are coming back. So also, if you want to make some long-term decisions, you want to know that it's a common bottleneck that's coming back very frequently. And as I already mentioned, the residual space is very important, because if you want to do some metering of traffic, some buffering, doing some rerouting, you need to know where there is space available so that you can use that. And of course, you can use it for the real-time monitoring of bottlenecks, which is then really important for the real-time traffic management systems. So that's about the introduction of how it's going in Rotterdam and what are the goals of Emeralds and the use case within Rotterdam. Next step is a bit of an explanation on how the automated system is working. So if we talk about automatic network management, we also often say that it's integrated network management, and the definition is that we want to manage the traffic by coordinating different traffic management measures, and also to take the situation at the right level. So either local sub-network or network level, you want to do it at the right scale. The measures that we talk about can be either intersection control, ramp metering, in-car systems, and that's a large variety of systems that can be used. It can be rerouting, but also speed assistance, for example. Another measure is a variable speed limit, which is potentially very effective on highways. However, it's not that often implemented on highways because of the implementation issues that you can have. And you have dynamic route information where you can reroute vehicles. So the situations that you can assess with it are also multiple. So for example, you have the urban networks where you can steer towards delays, livability, or multimodal problems where you have interactions between modes that needs to be addressed. On the highways, it's actually two types of congestion that you can tackle. It's either the standard bottleneck, which, for example, can occur when you have a lane drop or an on-ramp, but also shock waves which are moving jams that can travel very large distances over your highway network, and that can so it can initiate maybe 20 or 30 kilometers downstream, and it walks upstream traffic and causes a lot of delay, but also a lot of unsafety. But because those jams are often the jams where you come to a complete standstill, you do not have a typical cause, or you do not know the origin of the shockwave, so it can be quite abrupt. So also quite a lot of incidents happen within those shockwaves. And as mentioned, it can also be used to improve the tunnel safety. How it works is that there are standardized control algorithms algorithms that are completely specified and open, so it's no black box approach. It's based on traffic flow theory principles. For example, if we can reduce the congestion at the start of the rush hour, we have a reduction of the queue length for the complete rush hour. So that means that there's an accumulation of profit that you can keep for the whole afternoon, so to say. The system is easy to configure and to adjust. It's autonomous and robust. There is error handling, and the system will automatically decide when there are, for example, too many errors that it needs to shut down. And there are quite some visualizations and some advanced data-driven tools that can either be used for evaluation or for testing new configurations or features within the system. So how does this work around the tunnel in Rotterdam? So in the middle is the tunnel, and if there is a problem, for example, there can be a queue that's going to spill back into the tunnel, then the first thing that we can do is increase the outflow of that queue to reduce the size. So that's the first thing that we try to do. And if that's not helping, we can also reduce the inflow. And that means that the flow in the tunnel is reduced by either increasing the outflow or by reducing the inflow. So as mentioned, this is done for tunnel safety, but you can also replace the tunnel for a corridor with air quality problems, or where you have crossability problems for the active modes for the pedestrians and the bicycles. So several goals can be used for this system. And then there are quite some control principles that are all defined with these algorithms. It's using the available space, which is defined by the policy framework, and it uses it efficiently. It aims to establish a fair distribution of queues throughout the network, so that not only one route is affected, but that the traffic is spread out through all the different routes that are in the network. And it reacts on the actual effects on the control. So it's PID feedback control, which means that it continuously measures the effect of the control measures on the traffic situations on the queue lengths in this case. And we adjust the signal settings by using delta green time. So that means that it can either be like plus 10 seconds or 10 seconds less of green time. And that also allows the local intersection controller to also vary their own local green times by not directly setting you need a 20 or 30 second green time. We only impose a delta green time based on their own basic local green time. So one of the most important monitoring aspects of this INM system is queue estimation. And I'm going to tell a bit more about how we're improving that within Emeralds now. The goal of this queue estimation is to determine the amount of residual space, the queue length, and several other indicators that can be derived from radar data. So we now use radar data to do this queue estimation, and it's great data. It gives a lot of measurement points per second. So we have very detailed information on when there is a queue, where the queue is, where we have some residual space. However, it's also really costly to install. It's about 15K to install one, and then also you might need 2 for one road section, and also there's a lot of maintenance for these radars, which is also significant work and cost. So the high cost and maintenance are really now the cause that this integrated network management system is not rolled out more widely. So the aim of this Emerald is to replace the radar-based queue estimation with a more cost-effective solution. And what we use now is two main data sources. So we have minute aggregated floating car data, AFCD. It's available for around every 50 meters for all of the roads in the Netherlands, actually. And so it's quite detailed. It has some problems because it's a bit lagging because it's using the up to the last 30 vehicles that pass there, so it can be a bit behind in time, but the level of detail is quite high. And the second data source that we use is the traffic count from the induction loops. So those are the induction loops that are at the stop line of each of the intersection, and we are looking at the downstream loop detectors, but also with the upstream loop detectors. And yeah, we developed a method to combine those two sources and to improve the estimation. And yeah, we tested them against two different baseline models, and the new model, which is AI-based, really outperforms the other ones. It provides high accurate Q estimations, and also so in the INM system, we use those Q estimates to determine if there is a active bottleneck in the system, and also identifying bottlenecks and hotspots based on those Q lengths is very well possible. So that's nice. So I will show a bit on how it's done. So this is, first I will show the two baseline models that we use. So here is the first baseline where we detect the end of the queue based on a speed drop. So what you see here is real floating car data. So these are real trajectories from vehicles. And what you can see, every dot is a vehicle, and I don't like the colors that much. I would have changed them, but the red ones are the fast ones and the blue ones are the slow ones. This is coming from the article of the baseline. And what you can see with the black line, it's the place where they where a speed drop is identified. So also see that the vertical axis is space in this, and this is kilometers. So this is quite a long area. And normally we want to have a Q length that's maybe with the accuracy of about 50 meters. So you can see that here the scale is a bit larger than we would like it to have. The second baseline is using trajectories and then see if we can determine the ISO speed contours. But of course we have the aggregated floating car data. So what we did is we emulated trajectories by more or less shooting vehicles through the time-space diagram and see how they evolve. And then based on those emulated trajectories, we can create some ISO speed contours. And that can then also be the basis for another baseline model. So looking at the comparison between our approach and the baseline approach, we can see quite some improvements. On the top, we can see the first baseline where we use the observed speed drop. And then the blue line is the ground truth. So the ground truth, we use it here. It comes from the radar system. The baseline is the pink dashed line, and the green line is our approach. And yeah, I think also already visually you can see that the green line matches the ground truth much better than the baseline model. And that also holds for different ISO speed contour plots, which are shown in the lower level. Yeah, there's actually a lot of difficulties by getting these speed contour plots working quite well. So we do see some increase and decrease when there is a congestion, but also there's a lot of problems when there is a large queue, for example, with a lot of more or less constant speeds within the queue. Then a bit of statistics. So the green one is our model, and the blue and red ones, those are the baseline models. And you can see here the distribution of the different errors. And you can see that for different days, and especially like on a Tuesday, then we have a lot of congestion. You can see that the new model outperforms the other ones, and that the average error is below 15 meters, which is very acceptable for the application in traffic management. So we are really happy with those results. Then the next topic will be the multimodal intersection analysis. What we want to do here is that there is a lot of data available for the city of Rotterdam, and we want to support the city in monitoring their multimodal traffic performance. And they have the ambition to build their own Power BI dashboard. They have a data analytics team that can work on it. And also they have a lot of data. So they have the intersection data where we have the waiting times and the flows for each of the modes. It's available for every 50 minutes, and it can be exported automatically or daily from their JAFC, which is a traffic management control analyzing program, but it does not allow to do large-scale analysis for the whole network. So what we are going to do is we're going to help them. Which indicators do they need to use? How do they need to aggregate it? Which intersections in time and space do we need to look at to get a good insight in how their multimodal network is performing? It helps them to implement their multimodal mobility policy. And they already have some reference framework, so we can help them managing it. So we built some, this is their multimodal network framework that they have. So they do have networks for each of the different modes. So the different colors correspond to different modes, and they also have defined this for different levels. So they have the primary network, which is the most important one. Then they have the secondary and the tertiary levels, which are less important. So also the thresholds for waiting time are much higher for the secondary and the tertiary road levels compared to the primary ones. What we did, we built some mock-up dashboards where we have tested a lot of different indicators and different aggregation levels. So what we did, we have a simple dashboard that just shows you how the distribution of modes and networks is. So that's quite simple. And we have, for example, a indicator that shows the compliance. That's the amount of time that the performance of the network is better than the threshold value. And we can do that for either the modes or the primary, secondary, tertiary networks. Then we make a simple list of the best and the worst intersections that we have in the network. And there's also a ranking of the different modes within the network that we are then testing. So this is just an overview to give them a bit of an idea. And I think we still need to work a bit on bridging the gap between this very high level overview and the very much more detailed data, because here you can see for each of the different signal groups, for each of the different intersections, you can see that, for example, this one is intersection 15/40, signal group 24, it's the bicycle, it's a primary network, it has an average flow of 1300, and then we have quite some indicators showing on how it performs. So they have a minimal performance, the minimum performance threshold is 60 seconds. So they want that all the primary bicyclists on this road have a waiting time less than 60 seconds. and they have a desired waiting time of 45 seconds or less. And we can see that the compliance is only 38% for the minimal threshold and only 17% of the desired threshold. So we did calculate some different indicators for that. And you can also, for example, do this for the complete day or for the morning peak, evening peak, rest day. So you can do some different filterings to get some more insight. And finally, if you do have a signal group that's not performing very well, it's also able to do some more in-depth analysis. So this is just for one bicycle signal group. We can just see the flow, which is increasing and decreasing over the days. We can see the average waiting time for each of the 50 minutes and the maximum waiting time per 50 minutes. And then on the right, we see a lot of different indicators that we tested and discussed with Rotterdam to see which of those is best for their policy monitoring, so to say. Also, we go in the real details where we make heat maps, where you can see that on the left, you can see a heat map for flow and waiting time. So on the x-axis, you have the time of the day, so starting at midnight and then ending at midnight again. But then on the y-axis, we have all the days in the data set now, so which is now from November until April this year. And you can see how all the days perform in terms of flow and waiting time. And on the right, you can see more or less the same picture, but then the colors depict if it's green, if it's better than the desired waiting time. It's orange if it's worse than the desired waiting time, but better than the minimum waiting time. And red means that it exceeds the threshold for the minimum waiting time. So that's not good. So this is how we help the city of Rotterdam to analyze all their intersection data and do a multimodal analysis for that. Finally, a few minutes, I think, on the highway traffic prediction. So we have congestion propagation and breakdown prediction. For the integrated network management, it will really help if we can predict when a breakdown is happening or when a shockwave is coming towards the network. And we can support the automated traffic management systems, but we can also help the operators that are doing manual traffic management in the control centers. The available data is induction loop sensors. It's installed every 500 meters on the road, and it's measuring speed and traffic flow continuously. And this is a really rich data set covering the entire highway network. And then we used different AI methods to do the predictions. And we especially want to have the temporal and the spatial lag features around the to see what's happening around a specific measurement place in space and time. So we look a bit upstream and downstream back in time to have the short-term propagation of the traffic. The adjacency network and the configuration of the network is explicitly modeled within the system so that we can look at nearby loop detectors to find the correct information. And the feature set is carefully engineered and enriched with the geographic context. Also, weather data is, for example, included, and then gradient boosting algorithms are used to have a forecast that is very accurate. And also, so we aim for a very high precision, and then we are going to optimize the recall to have the most efficient forecast for traffic management purposes. And just to give a brief sneak peek on how that can look, so this is an example on how we have a prediction around a tunnel, and what you can see on the left is the ground truth, the measured speeds, and on the right we have the predicted speeds, and we have a start of the prediction at the dashed line. So everything on the right hand side right of the dashed line are the predictions ahead. And you can see that, for example, this shockwave is very well propagated through the network, and it was really able to do that. So also the queue that's below and the queue that's on top is also propagated pretty well. So we can see that regular congestion patterns are very well propagated through the network by this algorithm. However, we also have some difficulties. So this is, for example, a day when there was a incident or roadworks on the network. So you see a, more or less a continuous breakdown of traffic before the roadworks. And what you can see that in the ground truth, there is the congestion stays there, but the model itself is unable to see that there's a reduced capacity due to the roadworks. So the prediction is going to dissolve the queue and actually going back to free flow. So the non-recurring roadworks or incidents, they are not very well predicted with these types of model. But yeah, there are also some ideas to improve for that. These were the slides and the things that I want to show. So are there any questions?
Thank you very much, Erik-Sander. Thank you for your interesting explanation about this particular use case. Very interesting. We have some minutes left, so we can use for one particular questions that arrived. It was in the middle of your presentation, you talked about the queue estimation model that you used in Rotterdam. And the question is, how transferable is the Rotterdam queue estimation model to cities with different infrastructure layouts or data availability? And what are the minimum data requirements? I mean,
so the transferability is really interesting because you can see that road sections on urban networks, they all have different layouts and they have a lot of very specific characteristics and geometries. However, we have very good results for that in Rotterdam because we used several road sections for the training set, but we also excluded some road sections from the training set where we did have a ground truth, and we also tested the transferability for the model, and we also have quite good results on those data sets. So we now believe that if you have a road section where you have those floating car data and those loop detectors, we can transfer the model that was trained on some of the intersections in Rotterdam, and we can use it anywhere. The only requirement is that you need the loop detector data and the floating car data. And the testing results for transferability were quite good. Great.
Thank you very much, Erik-Sander. We actually reached 1 hour, so I'm afraid that we don't have more time to go through some other questions that arrived, but probably we can share with the audience after the webinar. Yeah. So I want to actually thank you for all the presentation, and thanks to all the panelists. I just want to add a few words about this organized webinar. So the webinar has been recorded, and the recording will be shared on the Emerald website and YouTube channel and our account. So also the slides will be shared after the webinar. So wait for it, because we'll make them at your disposal, and you have everything on the website. Thank you to all the panelists. So see you hopefully all on Friday for the next webinar that will be focused on another use case. And have a good day.
Thank you very much.
Thank you.
Thank you.
Thank you, Marialetizia, for organizing, and also to Sarah.
Thank you, everyone.
Bye-bye.
Thank you, everyone. Bye.